We have Matt Handford with a 5-minute talk. You can probably just start it when he starts his talk.
Okay, we're good to go? Yep, okay. So I'm going to give my presentation on human prosthesis interaction. It's basically what we're trying to do is answer the question, can we predict how a prosthesis will affect a person using metabolic optimization? The reason why we're trying to look at this is because if we can do this, we can predict what people are going to do with a prosthesis. This can lead to very rapid iteration in testing out different types of controllers for these prostheses. So what we did is we built a sagittal plane model of a person wearing a prosthesis. It's actuated using 13 union biarticular muscles, 8 on the unaffected side, only 5 on the affected side, with all of the muscles around the ankle replaced with a prosthesis torque motor. Now, in a previous study, we had that torque motor was governed by some cost function for the prosthesis, but in this case, we're constraining it to act via a series of very simple state-based controllers. Some linear stiffness for the initial stance phase, and then it pushes off with some added work strategy, either adding in a constant torque, changing the stiffness and set point, or maintaining some maximum torque. And we can also get it to be constrained to some passive device as well. Once we have our model with its prosthesis, we can define a walking gait by looking at basically saying a standard walking cycle can be divided into a series of contact phases based off of which heels and toes are in contact with the ground, and then we can transition between those contact phases using inelastic collision. Each of those contact phases we then break down further into individual segments which can be optimized individually, and then we use constraints to say that, okay, all these segments now have to be continuous, and we get a nice walking cycle out at the end. But if we're going to optimize, we need a cost function. For our cost function, we use a form of a metabolic cost based on Alexander and Minetti that uses activation, shortening velocity, and max isometric force of all the muscles over the entire stride. And we also add a very small cost for force rate, which kind of excludes a lot of the very erratic muscle force local minima that we tend to run into, and according to a couple of previous talks, may actually be really important for metabolic costs in general. So we can run this using a variety of initial seeds. Typically the optimization runs for about a half hour to 4 hours, depending on how nice it's being that day. But we can run it using all of our different controllers at a variety of different work levels. And when we do, what we get out is a relationship between net metabolic rate and our prosthesis work rate. Whereas we add in work with the prosthesis, we get a benefit with our metabolic cost. Now, our simulation predicts that this benefit, we should be able to beat a non-amputee. But obviously we don't see that in reality. We're at best just reducing it from a passive, say that SACH. I mean, we look at the experimental data and we're still well above the non-amputee. Well, we can look at some of the animations that come with each of these controllers. This is just a select level of work for each one of them. And it may be a little bit more difficult to see just from the animation itself, but all of these gaits are asymmetric. And they're asymmetric in that they favor the affected side. The person is spending more time on their prosthesis in order to make use of that free work. But again, we don't see that in an experiment. In experiment, we see relatively symmetric, or we see them favoring the unaffected side. And when we try to control for this in our simulation, say we enforce a symmetry constraint, we see that metabolic cost get bumped up. We can constrain symmetry kinematically using ground reaction forces, just step time, or a combination of all of them. But in every case, we get that increase in cost. And whether or not we constrain that symmetry, we actually agree pretty well with experimental kinematics and torque and angle data. We do have a couple of areas where we do see some pretty big differences, mainly in the affected knee torques and in the angle for the knee and prosthesis there, but that can be explained by the fact that we're not using the exact same controller that's being used in this experiment. So far we have an optimization with 3 different controllers correspond to, or predict the same work-cost relationship. Bilateral symmetry increases cost, and optimization and experiment give different results. So we have a bunch of ongoing and future work trying to look at different types of controllers, looking at different types of cost functions, and different types of model improvements. Since I'm out of time, I do have some preliminary results, but we can discuss those offline. Some animations like that. Any questions? Not yet.
You showed some Pareto fronts where you're adding more and more, I guess, mechanical work from the prosthesis, and you go down to a minimum, and then it starts coming back up again.
Yes.
So can you talk about like what happens if you keep adding more and more energy, if you keep climbing that curve, and why does it go up?
So I would speculate that we don't go much higher than that, but typically as we go up to those very high work rates, now we have the biological side has to kind of recover from that. Because this is doing a full stride, we're putting in a lot of work on one side, but we're also trying to maintain, in this particular instance, we're looking at a constant speed. So if we have all of this work, all of this torque going through on the prosthesis side, we kind of have the biological side that has to recover from that. Now I don't know how it would affect if we maybe increase the speed. Maybe we would see that would be still a decrease further, or if we affected things like that, allowed it to change velocity or stuff like that. But at this particular speed, adding that much work is going to be a detriment.
Okay, we have one more question in the back, and if the video presenters could come line up over here, that would be great.
Hey, over here. So you made note of the fact that like your current simulations suggest that prosthesis users are going to spend more time on their affected side, which is highly unlikely.
Yeah.
Do you think that you could maybe talk about the expected effect of maybe putting in like a confidence or something in that prosthesis? I know like from kind of interactions with users, one reason why they seem to not put, or they seem to favor their unaffected side is just they have more trust in that leg since they don't have like that motion in their socket or things of that nature. So I guess, have you thought about maybe adding, which is difficult, but maybe some of the more qualitative aspects and like giving that into your cost function and seeing how that changes your results?
So one of the things that we run into, obviously with optimization like this, is we can't really add in that noise and that instability, right, of having non-periodic gaits. This is predicting a perfectly periodic gait. So it's hard to talk about like distrust stability-wise. We could start looking at, some of the things we're looking at right now are things like socket loading penalty functions, things like that, where maybe there's pain or pistoning or something going on in their socket that is something that they don't want to have happen, like high normal forces, high shear forces, or rotations. And so they're going to distrust that a little bit more, walk on the unaffected side more. And some of it also could just be training, is that they're not used to walking on something that they can't feel. They can't feel the ground with the prosthesis, so they're still working with the leg that can feel the ground, and with enough training, with enough work with a prosthetist, they might learn to trust that limb a little bit more.
I guess just real quick follow-up to that. For the data that you're using then, do you know if that data is coming from naive prosthesis users, or is that from like generally people who have had an amputation for 5-10 years or something, and therefore have like a certain confidence, or at least know what they're getting out of their prosthesis?
So all this data comes from Casada and Collins, 2016. They did use prosthesis users who I believe had amputation for at least a year, if not more than that. And they had a training period on that particular device. So not completely naive, but it is a novel device, and so I would imagine trust would still be an issue.
Okay, cool.
Great, thanks, Matt. Next up.